Hey everyone, and welcome. Today we're diving into graphene, but I want you to think about it a little differently. Don't picture just one material. Instead, imagine it's a super high-tech construction set, a box of carbon building blocks with just unbelievable potential. We're going to see how scientists can assemble, disassemble, and then rebuild these blocks to create totally new materials. Let's jump right in.
So this is really the big question, isn't it? We all know what graphite is. It's literally in the pencil on your desk. It's cheap, it's abundant. So the real challenge is, how do you take this everyday stuff and transform it into a mind-blowing super material? One that could change everything from our electronics to our medicine. That's what we're going to unpack.
And the answer, you might be surprised to hear, follows a really elegant three-step playbook. You build it, you break it, and then you repair it. The whole idea is to start with a basic material, you intentionally damage it in a very specific way, and then you reconstruct it into something way more powerful. It's a story of controlled destruction and clever creation, all happening at the molecular scale.
Okay, so let's start with Act 1, building the set. Before we can break anything, we first need to get to know our building blocks. And you see, it's not just one thing called graphene, it's a whole family of materials. You can really think of it as a carbon Lego set.
First up, we've got the crown jewel of the set, monolayer graphene, or SLG. This is the perfect stuff. It's that flawless, honeycomb sheet of carbon that's only a single atom thick. It's the strongest, most conductive version, literally the stuff of scientific dreams. But as you can probably guess, making these perfect sheets is incredibly tough and very, very expensive.
Next in the box are graphene nanoplatelets, also known as GNPs. Think of these as kind of messy little stacks of 10 or more graphene layers bundled together. They're basically just ultra-thin flakes of graphite, and this makes them absolutely perfect for mixing into other things like plastics or resins to create super strong and lightweight composites.
And finally, we have the tiniest members of the family, graphene quantum dots, or GQDs. These are teeny tiny, nano-sized fragments chopped off a graphene sheet. But here's where it gets really wild. Because of quantum mechanics, these little dots actually glow. They fluoresce when you shine a light on them, which is opening up incredible possibilities for things like medical imaging and next-gen displays.
Okay, so not every piece in our carbon Lego box is a flat sheet. Now we're going to look at a completely different shape, a really unique, super cost-effective, and spherical member of this carbon family.
This stuff is called onion-like carbon, or OLC. And the name is perfect, because its structure is made of these concentric spheres of carbon, all nested one inside the other. It's just like a Russian matryoshka doll, or, the layers of an onion. And this unique shape gives it some really useful properties.
So, how do you make these little carbon onions on the cheap? Well, you can forget about expensive lab-grade materials. The modern way is something called pyrolysis, which is just a fancy science term for heating something up without any oxygen. You can take cheap waste products like wood or old plastic, you bake it, add a catalyst, and the carbon atoms just naturally curl up into these perfect little spheres. It's a seriously efficient way to turn trash into treasure.
All right, so we've built our Lego set. Now for Act 2, we're going to break it. This is where the story takes a really fascinating turn. We're going to talk about graphene oxide, a material that is, for all intents and purposes, a deliberately spoiled or broken version of graphene.
And that, of course, leads to the obvious question. Why on earth would you take a near-perfect material and intentionally mess it up by sticking a bunch of oxygen all over it? I mean, it seems completely backwards. But as we're about to see, this flaw is actually its greatest strength.
The key to making tons of graphene oxide is a process called Hummer's method. You start with simple, cheap graphite powder. First, you mix it with some really powerful oxidizing acids. These chemicals then literally force their way in between the layers of graphite, wedging them apart and making the whole thing swell up. And then for the final step, a blast of ultrasound. High-frequency sound waves shakes everything loose, separating the stacks into individual graphene oxide sheets just floating around in a liquid.
And here's the crucial trade-off. You see, pure graphene is an amazing electrical conductor, but it's expensive to make and it absolutely hates water. It's insoluble. Our broken version, graphene oxide, is the complete opposite. It's an electrical insulator, but it's super cheap to make in huge quantities, and it dissolves perfectly in water. And that ability to just dissolve in water, that's the superpower that makes everything that comes next possible.
And that brings us to our final act, the repair. We've taken cheap graphite, we've broken it apart into these easy-to-use graphene oxide sheets, and now we're going to fix the damage to create an entirely new, incredibly useful material. This right here visualizes our entire journey perfectly. On the left, you've got that perfect graphene lattice. In the middle is our deliberately defective graphene oxide, all cluttered up with oxygen groups. And then on the right, you have our final repaired product, reduced graphene oxide, or RGO. As you can see, most of that oxygen is gone and that beautiful conductive carbon structure is back.
So how do we actually do this molecular repair job? How do we strip away all that oxygen to get the electrical conductivity back? Well, it turns out scientists have three main tools in their toolbox for this. The first way is through chemical restoration. This means using chemicals called reducing agents. Some are pretty harsh, like hydrazine, but others are actually much more eco-friendly, like ascorbic acid, which is basically just vitamin C, to chemically pluck the oxygen atoms right off the graphene sheet. The second method is pure brute force, thermal restoration. You just take the graphene oxide and bake it in a furnace at over 1,000 degrees Celsius. The intense heat forces those oxygen atoms to break off and escape as carbon dioxide gas, leaving a much cleaner, much more conductive graphene sheet behind. And finally, we have the most precise and, let's be honest, the absolute coolest method, laser restoration. With this, you can take a thin film of insulating graphene oxide and use a standard laser to literally write a conductive circuit right onto it. The focused energy from the laser beam instantly vaporizes the oxygen exactly where it hits, turning that spot from an insulator into a conductor in a flash. This means you can print flexible electronics directly onto almost any surface you can think of, paper, plastic, you name it.
So, there you have it. We've seen how this simple build, break, and repair philosophy can turn cheap, everyday carbon into a whole family of advanced materials. And that leaves us with a much bigger question to think about. If this powerful idea works so well for carbon, what other materials could we engineer this way? What's the next common element just waiting for its own set of build, break, repair instructions? It's a fascinating thought. Thanks for joining me.